Right now, at this very second, you are not sitting still. You are not standing still. Nothing about your existence is stationary. The chair beneath you, the ground beneath that chair, the continent beneath that ground, the planet beneath that continent, all of it is moving. Earth is spinning on its axis at roughly 1,670 kilometers per hour at the equator. But that rotation is nothing compared to the speed at which Earth is orbiting the Sun, approximately 107,000 kilometers per hour. And even that is a gentle stroll compared to the speed at which our entire solar system is hurtling around the center of the Milky Way galaxy. About 828,000 kilometers per hour. You are, right now, traveling through space at a speed that would carry you from New York to Los Angeles in less than 20 seconds. But here is where things get truly unsettling. All of that motion, the spinning, the orbiting, the galactic rotation, all of it is happening inside something much larger. Our galaxy, the Milky Way, is itself moving through space. And it is not drifting aimlessly. It is heading somewhere very specific. It is heading toward a collision, not with an asteroid, not with a rogue planet, not with a star, with an entire galaxy. A galaxy that contains roughly 1 trillion stars, a galaxy that spans 220,000 light-years across. A galaxy that is, at this exact moment, closing the distance between us at a speed of approximately 110 kilometers every single second. That is nearly 400,000 kilometers per hour, and it has been doing this for billions of years. The name of this approaching giant is the Andromeda Galaxy. You might have heard of it. It is the nearest large galaxy to our own. It sits roughly 2.5 million light-years away from us, which sounds like an impossibly vast distance. And it is, but in the language of galaxies, in the timescales of cosmic evolution, 2.5 million light-years is practically next door. And Andromeda is not just sitting there passively existing at that distance. It is coming toward us. It has been coming toward us for a very long time. And the question that has consumed astronomers for over a century, the question that was supposedly answered definitively in 2012, and then thrown wide open again in 2025, is whether or not it will actually hit us. But before we get to that answer, before we get to the groundbreaking study that changed everything scientists thought they knew, there is something you need to understand first, something that makes this story far more immediate, far more visceral than a collision that may or may not happen billions of years in the future. And that something is this: the Milky Way has already been hit. Not once, not twice, multiple times. Our galaxy has a long and violent history of collisions with other galaxies. Some of those collisions happened so long ago that only the faintest traces remain. Ghostly streams of stars on strange orbits, clusters of ancient stars with foreign chemical signatures, scars written into the very structure of the galaxy itself. And one of those collisions is not ancient history at all. One of them is happening right now. As you listen to these words, a smaller galaxy called the Sagittarius Dwarf is in the process of being torn apart by the Milky Way's gravity, its stars being ripped away and scattered into long ribbons that wrap entirely around our galaxy like a cosmic thread being unwound from a spool. We are, at this moment, in the middle of a galactic collision. Most people have no idea. So this is not a story about something that might happen in the distant future. This is a story about something that has happened before, is happening now, and may or may not happen again, on a scale so massive it is difficult for the human mind to truly comprehend. This is the story of our galaxy, where it came from, what it has survived, what is bearing down on it right now, and what the future holds. And I need to tell you up front, the answer to that last question changed dramatically in 2025, and the new answer is far more uncertain, and in many ways far more fascinating than anyone expected. If you are the kind of person who looks up at the night sky and feels something stir inside you, a sense of wonder, a sense of smallness, a sense of wanting to know what is really going on up there, then this is for you. Subscribe to this channel and hit the bell icon, because we are going to go deep. We are going to go all the way from the formation of the Milky Way itself to the cutting edge of modern astrophysics. Drop a comment right now and tell me, do you think Andromeda will hit us or miss us? I want to know your instinct before we get into the science. And if you have already decided to stay for the whole journey, write the word collision in the comments so I know you are here for the full ride. Let us begin at the beginning. To understand why the Milky Way might collide with Andromeda, you first need to understand what the Milky Way actually is, not in the vague poetic sense of a band of light across the sky, but in the precise, structural, physical sense. What is this thing we live inside of? The Milky Way is a barred spiral galaxy. That means it has a flat, rotating disk of stars, gas, and dust, with a dense central bulge at its core, and sweeping spiral arms that extend outward from a central bar-shaped structure. If you could somehow fly above the Milky Way and look down on it from a distance, you would see something breathtakingly beautiful. A vast pinwheel of light, with bright spiral arms wound around a glowing center. The whole thing slowly rotating like a cosmic whirlpool. The disk of the Milky Way stretches approximately 100,000 to 180,000 light-years across, depending on where you define the edge. Recent data from the European Space Agency's Gaia spacecraft has pushed that estimate further outward than older measurements suggested, revealing that the outer disk extends further than astronomers once believed. The disk itself is relatively thin. The main visible disk is only about 1,000 to 2,000 light-years thick, though there is a puffier component, called the thick disk, that extends up to around 12,000 light-years above and below the midplane. We will come back to that thick disk later, because its origin is one of the most dramatic chapters in the Milky Way's collision history. Within this disk, there are several major spiral arms: the Perseus arm, the Sagittarius arm, the Scutum Centaurus arm, and the outer arm are the primary ones. Our solar system sits in a relatively minor structure called the Orion arm, sometimes called the Orion spur, which is located between the larger Perseus and Sagittarius arms. The spiral arms are not solid structures like the spokes of a wheel. They are density waves, regions where stars, gas, and dust are temporarily bunched up more closely together, like a traffic jam on a highway. Stars move in and out of the spiral arms as they orbit the galactic center. The arms themselves persist as a pattern, even though the individual stars within them change over time. At the very heart of the Milky Way, at its gravitational center, sits an object of extraordinary power and darkness. It is called Sagittarius A star, written as Skr A with an asterisk, and it is a supermassive black hole. Its mass is approximately 4 million times the mass of our Sun. That was confirmed by the Nobel Prize-winning work of Reinhard Genzel and Andrea Ghez, who spent decades tracking the orbits of stars, whipping around the galactic center at incredible speeds, proving that only a supermassive black hole could explain their motions. Sagittarius A star spans roughly 23.5 million kilometers in diameter, which sounds enormous until you realize that the galaxy it anchors is 100,000 light-years across. The black hole is a tiny, dense point at the center of an incomprehensibly vast structure, and despite its enormous mass, Sagittarius A star is relatively quiet. It is not actively consuming large amounts of matter right now. Compared to the blazing quasars and active galactic nuclei at the centers of some other galaxies, our supermassive black hole is sleeping. But it has not always been asleep, and it may not stay asleep forever. Now, everything I have described so far, the stars, the gas, the dust, the spiral arms, the central bulge, the black hole, all of that makes up only a small fraction of the Milky Way's total mass, roughly 5%. The other 95% is something we cannot see, cannot touch, cannot detect with any telescope that looks for light. It is dark matter. Dark matter does not emit light. It does not absorb light. It does not reflect light. It interacts with normal matter in only one way that we have been able to detect, through gravity. And it is everywhere. The Milky Way is embedded in an enormous, roughly spherical cloud of dark matter, called the dark matter halo. This halo extends far beyond the visible disk of the galaxy, roughly 1 million light-years across, which is about 10 times the width of the visible disk. The total mass of the Milky Way, including this dark matter halo, is approximately 1 trillion solar masses. That number, 1 trillion, is based on the consensus that has emerged from studies using Gaia spacecraft data over the past several years. Within just the inner 20 kiloparsecs of the galaxy, the dark matter alone accounts for approximately 137 billion solar masses. This invisible scaffolding of dark matter is not some minor footnote in the story of the galaxy, it is the dominant player. It is what holds the galaxy together. It is what determines the galaxy's gravitational reach. And as we will see, it is the dark matter halos of galaxies that play the most critical role when galaxies collide. The collision of two galaxies is, fundamentally, the collision of two dark matter halos. The Milky Way does not exist in isolation. It is part of a community of galaxies called the Local Group. The Local Group is a collection of roughly 80 known galaxies, with perhaps more than 100 in total once you include the ones that have not yet been discovered, hiding behind the obscuring dust of the Milky Way's own disk, or lurking too faintly to have been detected. The Local Group spans about 10 million light-years across and has a characteristic shape that astronomers describe as a dumbbell. Two concentrations of galaxies connected by a bridge of smaller ones. At one end of the dumbbell sits the Milky Way and its satellite galaxies. At the other end sits the Andromeda Galaxy and its satellite galaxies. These two giants dominate the Local Group. They are the gravitational anchors around which everything else orbits. The third largest member of the Local Group is the Triangulum Galaxy, also known as M33. It has a mass of roughly 300 billion solar masses and is generally considered to be a satellite or companion of Andromeda, though its exact orbital relationship is still debated. The fourth most massive member is the Large Magellanic Cloud, a satellite of the Milky Way with a mass of about 150 billion solar masses. These four galaxies, the Milky Way, Andromeda, Triangulum, and the Large Magellanic Cloud, are the heavyweights of the Local Group. And as we will discover, all four of them play crucial roles in determining whether or not the Great Collision will happen. There is one more thing you need to understand about the Local Group before we move on, and it is critically important. The universe is expanding. Galaxies across the cosmos are moving away from each other as space itself stretches. But that expansion operates on very large scales, hundreds of millions to billions of light-years. On the local scale, within galaxy groups and clusters, gravity is stronger than the expansion of space. The Local Group is gravitationally bound. The Milky Way and Andromeda are close enough and massive enough that their mutual gravitational attraction completely overwhelms any tendency for cosmic expansion to push them apart. In fact, their gravity is pulling them together. This is why Andromeda is approaching us rather than receding from us, while nearly every other galaxy in the universe is moving away from us, carried by the expansion of space. Andromeda is one of the very few that is moving toward us. Gravity has won the tug of war in our little corner of the cosmos. Now that you understand the stage, the Milky Way, its structure, its dark matter halo, its place within the Local Group, it is time to talk about the past, because the Milky Way you see today, the galaxy we call home, is not the galaxy that originally formed. It has been modified, reshaped, and rebuilt by a series of violent collisions, stretching back almost to the beginning of cosmic time. Our galaxy is a cannibal. It has consumed other galaxies. It has torn them apart and absorbed their remains. And the evidence of those ancient meals is still visible today, if you know where to look. In 2020, a team of astrophysicists, led by Diederik Kruisen at Heidelberg University, published a remarkable study in the monthly notices of the Royal Astronomical Society. They used artificial neural networks, a form of machine learning, to reconstruct the entire merger history of the Milky Way. Their tool analyzed the ages, chemical compositions, and orbital properties of the Milky Way's globular clusters, those ancient, dense balls of hundreds of thousands of stars that orbit in the galactic halo, because many of these globular clusters were originally born in other galaxies and then absorbed by the Milky Way when those galaxies were consumed. They carry within them the chemical fingerprints and dynamical signatures of their dead parent galaxies. By reading those fingerprints, Kruisen's team was able to build a family tree of the Milky Way, a genealogy of galactic cannibalism stretching back over 11 billion years. The earliest known major merger in this family tree involves a galaxy that the team nicknamed Kraken. Approximately 11 billion years ago, Kraken collided with and was consumed by the proto-Milky Way. At that time, the Milky Way was only about 1/4 of its current mass, which means Kraken was not a small snack. It was a substantial meal relative to the size of the galaxy that consumed it. Kraken contributed multiple globular clusters that still orbit the Milky Way today, identifiable by their characteristic low-energy orbits. This collision, happening when the universe was less than 3 billion years old, was one of the formative events in the Milky Way's early life. It helped shape the very foundation of our galaxy's structure. Yet, for billions of years, no one knew it had happened. It was only through the painstaking analysis of globular cluster properties, their ages, their metallicities, their orbits, that the ghost of Kraken was finally identified. An entire galaxy, consumed and forgotten, its remains hiding in plain sight among the stars of our own galaxy. But Kraken was just the beginning. The next major chapter in the Milky Way's collision history is perhaps the most dramatic of all. It is the merger with a galaxy known as Gaia Enceladus, also called the Gaia Sausage. This collision occurred approximately 8 to 10 billion years ago, and it was the last truly major merger the Milky Way experienced. The discovery of Gaia Enceladus was announced in 2 landmark papers in 2018. The first, by Amina Helmi and colleagues, was published in the journal Nature. Using data from ESA's Gaia spacecraft, Helmi's team identified a large population of stars in the Milky Way's halo that shared a common origin. They had similar chemical compositions, similar ages, and moved on similar orbits. These stars were not born in the Milky Way. They were the remains of a separate galaxy that had been devoured. Helmi named this ghost galaxy Gaia Enceladus, after the giant of Greek mythology. Independently, and almost simultaneously, Vasily Belakurov and colleagues at Cambridge identified the same structure and gave it a different name, the Gaia Sausage. The name came from the distinctive shape of the distribution of these stars in velocity space. When you plot their velocities, they form an elongated, sausage-shaped blob, reflecting the highly radial orbits on which these stars travel, plunging in toward the galactic center and back out again. The galaxy that became Gaia Enceladus was not small. It had a stellar mass of roughly 600 million solar masses, and its total mass, including dark matter, was perhaps 1/4 to 1/3 of the Milky Way's mass at the time of the collision. This was a head-on encounter between 2 substantial galaxies, and it left deep scars. The collision dynamically heated the Milky Way's pre-existing disk. Stars that had been peacefully orbiting in nearly circular paths were gravitationally kicked into more eccentric, inclined orbits. This is what created the Milky Way's thick disk, that puffed-up layer of older stars that sits above and below the thinner, younger disk. The thick disk is not a separate structure that formed independently. It is the bruised remnant of the original Milky Way disk, battered and swollen by the impact of Gaia Enceladus. The debris from the incoming galaxy now makes up a substantial fraction of the Milky Way's interstellar halo. The globular clusters it brought with it still orbit on characteristic paths. Its stars are identifiable by their lower metallicity and their distinct ratios of certain elements, the chemical DNA of a different galaxy, forever embedded in our own. The Gaia Enceladus merger reshaped the Milky Way. The galaxy before the collision and the galaxy after the collision were fundamentally different objects. The structure of the disk changed. The stellar halo was populated with foreign stars. New globular clusters were added to the inventory. Star formation patterns shifted. It was, in many ways, the defining event of the Milky Way's adolescence, a violent growing pain that transformed a young galaxy into something closer to what we see today. Between the era of Kraken and Gaia Enceladus and the present day, the Milky Way also consumed several smaller galaxies. The Helmi streams, discovered by Amina Helmi in 1999, represent the remnant of a dwarf galaxy that was torn apart by the Milky Way's tidal forces. Its stars now form coherent streams, rivers of stars flowing together through the halo on shared orbits, tracing out the path of their dead parent galaxy like a ghostly afterimage. The Helmi streams were among the first direct pieces of evidence that the Milky Way was assembled, at least in part, through the accretion of smaller galaxies. Another absorbed galaxy, known as Sequoia, contributed additional stars and globular clusters to the halo. The stars from Sequoia are identifiable because they move on retrograde orbits. They orbit the galactic center in the opposite direction to the rotation of the Milky Way's disk. This is a dead giveaway of foreign origin. Stars born in the Milky Way's disk orbit in the same direction as the disk rotates. Stars on retrograde orbits almost certainly came from somewhere else, captured and incorporated when their parent galaxy was destroyed. The ordering of these mergers, as reconstructed by Cruikshan's team, goes roughly like this. Kraken was consumed first, approximately 11 billion years ago. The progenitor of the Helmi streams came next. Then Sequoia, then Gaia Enceladus, the last great merger around 8 to 10 billion years ago. And then, after Gaia Enceladus, the Milky Way entered a relatively quiet phase. Just the slow, steady process of building up the thin disk, forming new generations of stars, evolving into the galaxy we see today, until, that is, the Sagittarius Dwarf arrived on the scene. The Sagittarius Dwarf Spheroidal Galaxy, discovered in 1994 by Rodrigo Ibata, Gerard Gilmore, and Mike Irwin, is the galaxy that is colliding with the Milky Way right now. It had been hiding in plain sight for decades, obscured by the dense star fields of the galactic center. It sits on the far side of the Milky Way from our perspective, about 70,000 light-years from Earth. When Ibata, Gilmore, and Irwin found it, they realized it was extraordinarily close to the Milky Way, far too close to survive intact. The tidal forces of our galaxy were already tearing it apart. And not just slowly. The Sagittarius Dwarf has had a dramatic, violent, and extended interaction with the Milky Way. It has not simply been gently nudging up against our galaxy. It has been passing through it. Repeatedly. A study published in 2020 in Nature Astronomy by Tomás Ruiz Lara and colleagues used data from the Gaia spacecraft to reconstruct the star formation history of the solar neighborhood, and found striking evidence that bursts of star formation in the Milky Way's disk correlated precisely with the times when the Sagittarius Dwarf is believed to have passed through the galactic disk. Their analysis identified at least 3 distinct passages. The first occurred approximately 5.7 billion years ago. The second occurred approximately 1.9 billion years ago. The third occurred approximately 1 billion years ago. And some analyses suggest it may have been as recent as 500 million years ago, which places it remarkably close in time to the Cambrian explosion, the period in Earth's history when complex multicellular life suddenly diversified in the oceans. Now, I want to be very clear. There is no established causal link between the Sagittarius Dwarf's passage through the Milky Way and the Cambrian explosion. The correlation in timing is noted by some researchers, but it remains speculative. What is established is that each passage of the Sagittarius Dwarf through the Milky Way's disk compressed gas clouds through gravitational disturbance and triggered measurable bursts of new star formation. The Milky Way literally made new stars because it was being hit. As the Sagittarius Dwarf has been torn apart over these multiple passages, its stars have been stretched into 2 enormous tidal streams, long, arcing ribbons of stars that wrap completely around the Milky Way, encircling our galaxy like a ball of yarn being unwound. These streams are called the Sagittarius Stream, and they have been mapped extensively using data from multiple surveys. They are among the most prominent structures in the Milky Way's stellar halo. The Sagittarius Dwarf itself, what remains of it, is now a faint, diffuse, elongated cloud of stars, a shadow of what it once was. Within a few billion years, it will be completely absorbed. It is a galaxy in its death throes, and we are the ones killing it. This is the reality of our galaxy right now. It is not a serene, stable, unchanging structure. It is actively consuming another galaxy. It has done this before, many times, and each time it has been changed by the experience. The Milky Way's thick disk exists because of Gaia Enceladus. Its stellar halo is populated with the ghosts of Kraken, the Helmi stream's progenitor, Sequoia, and others. Its recent star formation history bears the fingerprints of the Sagittarius Dwarf's repeated impacts. Every major feature of the galaxy you can observe, from the distribution of old stars in the halo to the ages of stars in the solar neighborhood, carries the memory of these collisions. The Milky Way is not a pristine creation. It is a composite, a patchwork, a Frankenstein's monster, stitched together from the remains of every galaxy it has consumed. And this brings us to the big question. The Milky Way has survived all of these collisions because the incoming galaxies were smaller, some much smaller, some moderately smaller, but none comparable in size to the Milky Way itself. What happens when the incoming galaxy is not smaller? What happens when it is the same size, or possibly even bigger? What happens when the Andromeda galaxy arrives? To answer that, we first need to understand Andromeda, what it is, how big it is, and how we know it is coming. The Andromeda Galaxy, officially designated Messier 31 or M31, is the nearest large galaxy to the Milky Way. It is located approximately 2.5 million light-years from us in the constellation Andromeda, and it holds the distinction of being the most distant object that can be seen with the naked human eye. On a dark, clear night, far from city lights, you can look up and see it. A faint, elongated smudge of light, barely perceptible but unmistakably there. What you are seeing with your unaided eyes is the combined glow of roughly 1 trillion stars, so far away that their light has been traveling through space for 2.5 million years before reaching your retina. When that light left Andromeda, the genus Homo had not yet appeared on Earth. Early hominins, Australopithecus and their relatives, were still walking the African savanna. Every photon of Andromeda's light that enters your eye tonight is a messenger from the deep past. Andromeda is a spiral galaxy, like the Milky Way, but it is bigger. Its disk spans approximately 220,000 light-years in diameter, roughly twice the diameter of the Milky Way's visible disk. It contains approximately 1 trillion stars, compared to the Milky Way's 200 to 400 billion. For many years, astronomers assumed that Andromeda was also significantly more massive than the Milky Way, perhaps 2 to 3 times more massive. But more recent studies have revised that estimate dramatically. When you include the dark matter halo, Andromeda's total mass is now estimated to be roughly 1 to 1.3 trillion solar masses, comparable to the Milky Way's 1 trillion solar masses. Andromeda is bigger in terms of visible extent and number of stars, but the total gravitational mass of the two galaxies is surprisingly similar. This matters enormously for the collision scenario, because the gravitational dynamics of the encounter depend not on the number of visible stars, but on the total mass, which is dominated by dark matter. Andromeda is tilted about 77 degrees from our line of sight, which means we see it nearly edge-on, a long, thin oval, rather than a face-on spiral. Its spiral arms, if seen from directly above, would be strikingly beautiful, perhaps even more pronounced than the Milky Way's. Like the Milky Way, Andromeda has its own history of collisions. There is evidence that it collided with at least one other large galaxy in its past. M32, one of Andromeda's current satellite galaxies, a compact, dense little elliptical galaxy, may be the stripped-down core of a once much larger galaxy that Andromeda consumed billions of years ago. The collision stripped away M32's outer layers, leaving only the dense nucleus behind. At the center of Andromeda sits a supermassive black hole that dwarfs our own. Its mass is estimated at approximately 100 to 140 million solar masses, roughly 30 to 35 times more massive than Sagittarius A star. Andromeda's nucleus is also peculiar. It appears to have a double nucleus labeled P1 and P2 by astronomers. This is explained by a model in which an eccentric disk of stars orbits the black hole, creating the appearance of two bright concentrations when viewed from our angle. If the Milky Way and Andromeda were to merge, these two supermassive black holes, ours at 4 million solar masses and Andromeda's at over 100 million, would eventually find each other at the center of the merged galaxy and begin a slow, inexorable spiral inward. But we are getting ahead of ourselves. The story of how we discovered that Andromeda is heading toward us is one of the great detective stories in the history of astronomy, and it begins more than a century ago. On September the 17th, 1912, at Lowell Observatory in Flagstaff, Arizona, an astronomer named Vesto Melvin Slipher turned the observatory's 24-inch telescope toward the Andromeda Nebula, as it was then known, and obtained its spectrum. Spectroscopy is the technique of spreading an object's light into its component wavelengths, like a prism splitting sunlight into a rainbow. By analyzing the spectrum of a celestial object, astronomers can determine its chemical composition, its temperature, and, critically, its motion. If an object is moving towards the observer, its light is compressed to shorter, bluer wavelengths. This is called blue shift. If it is moving away, its light is stretched to longer, redder wavelengths, red shift. By measuring how much the spectral lines of Andromeda were shifted, Slipher could determine how fast it was moving toward or away from us. What Slipher found was remarkable. The spectrum of the Andromeda Nebula showed a pronounced blue shift, indicating that it was approaching us at a velocity of approximately 300 kilometers per second. This was one of the highest velocities ever measured for a celestial object at that time, But here is what makes this discovery even more extraordinary. In 1912, nobody knew what the Andromeda Nebula actually was. The great debate about whether spiral nebulae were objects within our own galaxy or separate island universes far beyond it would not take place until 1920. Slipher measured the approach velocity of something he did not yet understand was an entirely separate galaxy. He had detected the motion of a trillion-star island of matter heading toward us, and he had done it more than a decade before anyone even proved it was outside the Milky Way. That proof came in 1923 and 1924, when Edwin Hubble used the 100-inch Hooker telescope at Mount Wilson Observatory in California to study the Andromeda Nebula in unprecedented detail. Hubble was searching for Cepheid variable stars, stars whose brightness pulsates in a regular cycle, with the period of pulsation directly related to the star's intrinsic luminosity. By measuring the period of a Cepheid's brightness variation, you can determine how intrinsically bright it is. By comparing that intrinsic brightness to how bright it appears in the sky, you can calculate its distance. It is a cosmic measuring tape. Hubble found Cepheid variables in Andromeda and measured their periods. The distances he calculated placed Andromeda far, far beyond the boundaries of the Milky Way, approximately 900,000 light-years away in his initial estimate, later refined to approximately 2.5 million light-years. The great debate was settled. Andromeda was not a cloud of gas within our galaxy. It was an entirely separate galaxy, vast and distant. And combined with Slipher's earlier measurement, the implication was now clear and stunning. A separate galaxy containing billions of stars, located millions of light-years away, was heading directly toward us at enormous speed. But there was a problem. Knowing that Andromeda is approaching us tells you only half the story of its motion. The blue shift tells you the radial velocity, the component of Andromeda's motion that is directly along the line between us and it, the toward or away component. But Andromeda could also be moving sideways, perpendicular to our line of sight. This sideways motion is called the transverse velocity, and it is measured by tracking how an object's position in the sky changes over time. Its proper motion. If Andromeda is coming straight at us, the transverse velocity is 0, and we are headed for a direct collision. If Andromeda has a significant sideways motion, it might miss us entirely, swinging past like a car in the next lane on a highway. The problem is that Andromeda is so far away that even a substantial sideways velocity produces an almost imperceptibly tiny movement across the sky. Imagine standing at one end of a football field and watching someone at the other end take a single step to the left. Now imagine that the football field is 2.5 million light-years long. That is the scale of the challenge. Measuring the proper motion of Andromeda is one of the most demanding observations in all of astronomy. For decades, astronomers could only estimate Andromeda's transverse velocity indirectly, using theoretical models and constraints from the dynamics of other galaxies in the local group. These indirect estimates suggested the sideways motion was probably small, but there was no direct measurement. Without a direct measurement, it was impossible to say definitively whether Andromeda would hit us or miss us. That changed in 2012, when a team led by Roland van der Merel, Sangmo Tony Sohn, and Jay Anderson at the Space Telescope Science Institute in Baltimore, Maryland, published the results of a painstaking study using the Hubble Space Telescope. Their approach was brilliantly simple in concept, but extraordinarily demanding in execution. They imaged fields of stars in Andromeda using Hubble in 2002, and then again in 2010, a baseline of 5 to 7 years. By comparing the positions of thousands of Andromeda stars in the two sets of images, using hundreds of distant background galaxies as a fixed reference frame, they could measure the incredibly tiny shift in position. The background galaxies are so far away, billions of light-years, that their own proper motions are essentially 0. They serve as a stationary backdrop against which Andromeda's motion can be detected. The precision required was staggering. They needed to measure movement smaller than a single pixel on Hubble's camera. They achieved this by averaging the positions of thousands of stars, reducing the statistical noise to the point where the incredibly faint signal of Andromeda's proper motion could be extracted. The result, published in May 2012 in the Astrophysical Journal, was dramatic. The transverse velocity of Andromeda relative to the Milky Way was found to be very small, less than approximately 17 kilometers per second, consistent with 0 within the measurement uncertainties. The radial approach velocity, confirmed at approximately 110 kilometers per second, was overwhelmingly dominant. The orbit was nearly radial. Andromeda was coming almost straight at us. Van der Merel and his team ran simulations based on these measurements and concluded that a collision was essentially certain. Their models showed that the Milky Way and Andromeda would have their first close approach in approximately 3.9 to 4 billion years, with a full merger completing around 6 billion years from now. They included the Triangulum Galaxy, M33, in some of their simulations, and found that it would likely be swept up in the merger as well, eventually falling into the combined galaxy. The merged remnant was given the nickname Milkomeda, a blend of Milky Way and Andromeda, and the consensus was that its formation was as inevitable as, in the words attributed to Benjamin Franklin, death and taxes. This became the standard narrative. It was published in textbooks. It was featured in NASA press releases, documentary films, and popular science articles worldwide. The Milky Way and Andromeda were on a collision course, and nothing could change that. The future of our galaxy was sealed. For 13 years, that was the accepted answer. Then, in June 2025, a study was published in the journal Nature Astronomy that shook the foundations of that certainty. The lead author, an astronomer at the University of Helsinki in Finland, with collaborators from Durham University in the United Kingdom, the University of Toulouse in France, and the University of Western Australia. The title of the paper was blunt and provocative: No Certainty of a Milky Way-Andromeda Collision. To understand what Sawala and his team did, and why their result is so different from the 2012 conclusion, you need to understand a critical distinction. When Van der Merel's team in 2012 predicted the collision, they used the most probable values for each of the measurements involved: the best estimate for Andromeda's distance, the best estimate for its velocity, the best estimate for the masses of the galaxies, and ran their simulations with those fixed numbers. When you plug in the single most probable value for every variable and run the simulation forward, you get a collision. That is what they reported. And it was perfectly valid as far as it went. But every one of those measurements has an uncertainty. The distance to Andromeda is known to within a couple of percent, but that couple of percent at 2.5 million light-years translates to real meaningful uncertainty in the orbital trajectory. The proper motion measurement, while a stunning technical achievement, also carries error bars. The masses of the Milky Way and Andromeda are known only to within perhaps 20 to 30%, and there are other measurements that matter too. The proper motion of M33, the mass of the Large Magellanic Cloud, the distance to M33, the concentration parameters of the dark matter halos. In total, 22 different variables, each with its own measurement uncertainty, feed into the calculation. What Sawala's team did, for the first time at this scale, was to take all of those uncertainties seriously. Instead of using only the most probable value for each variable, they sampled randomly from within the known error bars of all 22 variables simultaneously, using a technique called Monte Carlo simulation. In a Monte Carlo simulation, you run the calculation thousands or tens of thousands of times, each time drawing a slightly different set of input values from the probability distributions of the measurements. Some runs might use a slightly higher Milky Way mass and a slightly lower Andromeda transverse velocity. Other runs might use a slightly greater distance to Andromeda and a slightly higher LMC mass. Each run produces a different outcome for the future trajectory of the galaxies. By running the simulation many thousands of times and looking at the distribution of outcomes, you can determine not just what the most likely outcome is, but how certain you can be about it. Sawala's team ran 100,000 Monte Carlo simulations, each one integrating the orbits of the four most massive local group galaxies: the Milky Way, Andromeda, M33, and the Large Magellanic Cloud, forward in time for 10 billion years. This was the most comprehensive study of the problem ever conducted, and the result was striking. In the full four-body system, including all four galaxies, a merger between the Milky Way and Andromeda occurred within 10 billion years in approximately 50% of the simulations. Half the time the galaxies merged, half the time they did not. The widely publicized textbook certainty collision had become a coin flip. Let me break down the specific results, because the details are important. When Sawala's team considered only the Milky Way and Andromeda as a two-body system, ignoring the effects of M33 and the LMC, the merger occurred in slightly less than half of the simulations. Even without the complicating effects of the satellite galaxies, the measurement uncertainties alone were enough to make the outcome uncertain. When they added M33, the Triangulum Galaxy, to create a three-body system with the Milky Way, Andromeda, and M33, the merger probability increased to approximately 66%. M33's gravitational pull has the effect of reducing Andromeda's transverse velocity relative to the Milky Way, essentially helping to steer Andromeda more directly toward us. M33 is, in effect, an accomplice that makes the collision more likely. But when they added the Large Magellanic Cloud instead, creating a three-body system with the Milky Way, Andromeda, and the LMC, the merger probability dropped to only about 36%. The LMC has the opposite effect. As it orbits and falls into the Milky Way, the LMC's gravity tugs the Milky Way slightly off its current path. At its current orbital phase, the LMC makes the measured transverse velocity between the Milky Way and Andromeda appear lower than it truly is. Over the next 1.5 billion years, as the LMC continues its orbit, it will accelerate the Milky Way, increasing the true transverse velocity relative to Andromeda. The LMC also introduces velocity perpendicular to the plane of the Milky Way-Andromeda orbit. It is pulling the Milky Way out of the orbital plane, potentially deflecting it away from a direct encounter. When all four galaxies were included in the full system, the effects of M33 and the LMC partially cancelled each other out, leaving a merger probability of approximately 50%. The coin flip. For those simulations that did result in a merger, the median time to merger was 7.6 billion years, significantly later than the 5 to 6 billion years that had been the standard prediction since 2012, and the probability of the dramatic scenario that had been most widely publicized, a direct head-on collision within 4 to 5 billion years, turned out to be only about 2%. One of the most striking findings was a clear bimodality in the outcomes. The simulations did not produce a smooth spectrum of results. Instead, they clustered into two distinct categories. In roughly half the cases, the galaxies came within about 200 kiloparsecs of each other, close enough for dynamical friction between their dark matter halos to sap energy from their orbits, causing them to spiral inward and eventually merge. In these cases, the merger was inevitable once the first close approach occurred, though it might take several orbits before the final coalescence. In the other half of the cases, the galaxies never came close enough for dynamical friction to take hold. They might have a distant flyby, passing 500,000 light-years or more apart, and then recede, their orbits never decaying. In these cases, the Milky Way and Andromeda would continue their gravitational waltz indefinitely, orbiting each other without ever merging, at least not within 10 billion years. The analysis also revealed which measurements have the greatest influence on the outcome. The proper motion of Andromeda, especially the component in declination, was by far the most sensitive variable. Small changes in the measured proper motion could swing the merger probability from near zero to above 90%. The masses of all four galaxies also mattered significantly. Higher masses for the Milky Way, Andromeda, and M33 made the merger more likely because stronger gravity means more dynamical friction and tighter orbits, while a higher mass for the LMC made it less likely because the LMC's deflection of the Milky Way would be greater. The distances to Andromeda and M33 contributed meaningful uncertainty as well. Even the relatively well-known line-of-sight velocities had some effect. Till Sawala himself summarized the situation with a remark that captures the irony perfectly. He said, "It's somewhat ironic that, despite the addition of more precise Hubble data taken in recent years, we are now less certain about the outcome of a potential collision. That's because of the more complex analysis and because we consider a more complete system." This is a point worth dwelling on. The 2012 result was not wrong in any conventional sense. Given the data available at the time and the analysis performed, the conclusion of a certain collision was reasonable, but it was based on a simplified model, 2 or 3 bodies, with fixed most probable values for each measurement. The 2025 result uses more data, more sophisticated modeling and, crucially, honestly accounts for the uncertainties that were always present, but had not been propagated through the calculations. Science did not suddenly reverse itself, it refined itself. The answer became more honest, more complete, and more humble. And the honest answer is, We do not know. The implications of this uncertainty extend beyond mere academic interest. The question of whether the Milky Way and Andromeda will merge is one of the most fundamental questions in local group cosmology. It determines the long-term fate of our galaxy, the eventual structure of the local group, and even the ultimate isolation of our cosmic neighborhood, as the accelerating expansion of the universe carries all other galaxy groups beyond the observable horizon. Whether we end up as Milkomeda, a giant elliptical galaxy, or as two spirals continuing to orbit each other in an eternal gravitational partnership, changes the entire narrative of our galactic future. Future measurements may resolve the uncertainty. Gaia is still operating and will release increasingly precise data in future data releases. Each improvement in the proper motion measurement of Andromeda will tighten the constraints. But Sawala's analysis revealed a sobering caveat. Even if the proper motion of Andromeda were measured perfectly, with zero uncertainty, the outcome would still depend on the masses and proper motions of M33 and the LMC, which have their own substantial uncertainties. The problem is not just one imprecise measurement. It is the accumulated effect of many imprecise measurements, all interacting in a complex gravitational system. Resolving the fate of the Milky Way will require precision improvements across many different observational fronts simultaneously. Now, there is an aspect of this story that often gets lost in the drama of the Andromeda question, and it is this. Regardless of whether Andromeda arrives or not, the Milky Way has another collision coming that is far more certain and far more imminent. The Large Magellanic Cloud is going to merge with the Milky Way. The Large Magellanic Cloud, or LMC, is visible from the southern hemisphere as a diffuse, cloud-like patch in the night sky. It is located approximately 160,000 light-years from Earth, a distance that has been measured with extraordinary precision to within 1%, using eclipsing binary star systems by Grzegorz Pietszynski and colleagues in a study published in Nature in 2019. The LMC has a mass of approximately 150 billion solar masses, making it by far the most massive satellite galaxy of the Milky Way. It is not a tiny dwarf. It is a substantial galaxy in its own right, with its own complex structure, its own star-forming regions, and its own satellite galaxy, the Small Magellanic Cloud. For many years, astronomers assumed that the LMC was a long-term satellite of the Milky Way, orbiting around it for billions of years on a stable, repeating orbit. But more recent studies, particularly those using proper motion measurements from the Hubble Space Telescope, showed that the LMC's velocity is too high for a bound, repeating orbit given the Milky Way's mass. The most likely explanation is that the LMC is on its first infall. It is approaching the Milky Way for the first time, falling in from a large distance on a highly eccentric orbit. It has not been here before. In 2019, Marius Kortun and colleagues at Durham University published a study in the monthly notices of the Royal Astronomical Society examining the future of the Milky Way LMC system. Their simulation showed that the LMC will merge with the Milky Way in approximately 2.4 billion years, with a 68% confidence interval of 1.6 to 3.6 billion years. This is much sooner than any possible Andromeda encounter, and it is far more certain. The LMC is close, it is massive, and it is on a collision course that is not subject to the same level of uncertainty as the Andromeda question. The consequences of the LMC merger will be significant. As the LMC plunges into the Milky Way and is absorbed, it will deliver a substantial amount of new mass and gas. Some of that gas may be funneled toward the center of the galaxy, where it could feed our currently dormant supermassive black hole, Sagittarius A star. If enough gas reaches the black hole, it could trigger a period of active accretion, causing Sagittarius A star to temporarily wake up and become an active galactic nucleus, a far cry from its current quiet state. The Milky Way's total mass will increase significantly. The structure of the disk may be perturbed, though the effects would be much less dramatic than a collision with Andromeda, because the LMC is considerably less massive than the Milky Way. And as we have already discussed, the LMC merger has an indirect but potentially critical effect on the Andromeda question. As the LMC spirals into the Milky Way, its gravitational influence subtly alters the Milky Way's trajectory through space, potentially deflecting it away from a direct encounter with Andromeda. The LMC is not just a passive satellite being consumed, it is an active gravitational agent, tugging on the Milky Way and reshaping the dynamics of the entire local group. The Sawala 2025 study showed that accounting for the LMC reduces the Andromeda collision probability from about 2/3 to about 1/2. The LMC may, in a cosmic sense, save the Milky Way from its larger neighbor, or at least make the encounter less certain. Let us now turn to a question that many people find both fascinating and comforting. What would actually happen during a galactic collision? Not in the abstract, but in the concrete physical reality of what occurs when two galaxies containing trillions of stars pass through each other. The word collision is in some ways misleading. When we hear it, we instinctively think of two objects smashing into each other, a car wreck, a meteor strike, two billiard balls clicking together. A galactic collision is nothing like that. The reason is simple. Galaxies are overwhelmingly empty space. The average distance between stars in the Milky Way is about 4 to 5 light years. To put that in perspective, if you shrunk the Sun down to the size of a ping pong ball, about 4 centimeters in diameter, the nearest star, Proxima Centauri, would be another small ball approximately 1,100 kilometers away. That is roughly the distance from London to Madrid. Now imagine the Milky Way at this scale. It would be about 30 million kilometers across. And within that vast expanse, the stars would be little balls separated by thousands of kilometers from their nearest neighbors. When two such structures pass through each other, the individual stars simply sail past one another, like two swarms of gnats, interpenetrating without any individual gnat striking another. The probability of any two individual stars physically colliding during a galaxy merger is essentially zero. This means that if the Milky Way and Andromeda were to merge, no star would crash into another star. No planet would be smashed by an incoming sun. The collision is not a destructive event in the way that terrestrial collisions are destructive. But that does not mean nothing happens. Quite the opposite. While stars do not collide, their gravitational fields interact profoundly. When two galaxies approach each other, their dark matter halos are the first to make contact. These halos, extending far beyond the visible boundaries of each galaxy, overlap and interpenetrate. The interaction between the dark matter halos produces a phenomenon called dynamical friction, essentially gravitational drag. As each galaxy moves through the other's dark matter halo, the gravitational pull between the galaxy and the dark matter particles it is passing through transfers orbital kinetic energy from the galaxy's bulk motion into the internal random motions of the dark matter particles. The galaxy slows down. Its orbit decays. This is the mechanism by which galaxies that initially fly past each other are gradually drawn back together, their orbits shrinking with each pass, until they finally coalesce. The tidal forces during a galaxy collision are also dramatic. As the two galaxies approach, the differential gravitational pull, the fact that the near side of each galaxy is pulled more strongly than the far side, stretches both galaxies out of shape. Long, sweeping tails and bridges of stars, gas and dust, are pulled from the outer regions of each galaxy, forming the spectacular tidal tails that are visible in photographs of colliding galaxies throughout the universe. The antennae galaxies, located about 45 million light-years away, are a stunning real-world example of this process in action. Two spiral galaxies in the midst of a collision, with two enormous tidal tails of stars streaming outward from the interaction region. These tails can extend hundreds of thousands of light-years into intergalactic space. During the collision, some stars are flung onto entirely new orbits. Some may be ejected from the merged galaxy altogether, sent sailing into intergalactic space as rogue stars, intergalactic wanderers with no galaxy to call home. Studies have estimated that in a Milky Way Andromeda merger, there would be approximately a 12% chance that our own solar system would be ejected from the resulting galaxy. A 50% chance suggests it would be swept out to a region roughly 3 times farther from the galactic center than its current position. But, and this is important, none of these gravitational reshufflings would physically disturb the solar system internally. The Sun and its planets are held together by their own gravity, which is enormously stronger than the tidal forces of a distant stellar encounter on the scale of a galactic collision. The Earth would continue to orbit the Sun, the Moon would continue to orbit the Earth, and the other planets would continue on their paths. The solar system would simply find itself in a different part of the galaxy, or possibly no galaxy at all. But its internal structure would be intact. Gas, unlike stars, can collide directly during a galaxy merger. Gas clouds in the two galaxies can slam into each other, and when they do, the gas is compressed to extremely high densities. This compression triggers intense bursts of star formation, a phenomenon called a starburst. We observe this in colliding galaxies throughout the universe. Galaxy pairs in the process of merging often show star formation rates 10 to 100 times higher than normal, isolated galaxies. Massive, luminous young stars, blue giants and supergiants, light up the collision region, along with the glowing nebulae of newly formed star-forming regions. However, in the specific case of a Milky Way Andromeda merger, the starburst would likely be relatively modest. The reason is timing. Both galaxies are gradually using up their gas reserves as they form new stars. By the time a collision might occur, at least 7 to 8 billion years from now in the median case, both galaxies will have significantly less cold gas available for star formation than they do today. The collision would still trigger some enhanced star formation, but it would not be the spectacular, blinding starburst seen in gas-rich mergers between younger galaxies. The long-term outcome of a major galaxy merger between two large spirals is, according to both numerical simulations and observations of other merged galaxies, the formation of an elliptical galaxy. The beautiful, ordered spiral arm structure of both galaxies would be destroyed. The disks would be disrupted. Stars that had been orbiting in neat circular paths within the disk would be scattered onto random, chaotic orbits pointing in all directions. The resulting galaxy, Milkomeda, as it has been nicknamed, would be a large, roughly spheroidal or ellipsoidal blob of stars, without the flat disk and spiral arms that characterize the Milky Way and Andromeda today. It would resemble the giant elliptical galaxies that sit at the centers of galaxy clusters, though it would probably have a somewhat lower stellar density in its central regions than typical ellipticals. Some simulations suggest that if enough gas survives the merger, the result could be a lenticular galaxy, disc-shaped but without spiral arms, or in rare cases, even a superspiral. But the most likely outcome is an elliptical. The supermassive black holes at the centers of both galaxies would eventually find each other. After the galactic merger is largely complete, the two black holes, Sagittarius A star at 4 million solar masses and Andromeda's black hole at 100 to 140 million solar masses, would orbit each other at the center of the new galaxy, spiraling inward over a period of hundreds of millions of years due to dynamical friction and interactions with surrounding stars. As stars pass near the black hole binary, they exchange energy with the black holes, gradually shrinking the binary's orbit. When the two black holes eventually get within about 1 light year of each other, gravitational wave emission takes over as the dominant mechanism for removing orbital energy. The black holes spiral together more and more rapidly, emitting gravitational waves of increasing frequency and amplitude, until they finally merge in a cataclysmic event. The merged black hole would have a mass of roughly 144 million solar masses. Gas falling into the black hole system during and after the merger could potentially power a luminous quasar or active galactic nucleus, releasing energy equivalent to hundreds of millions of supernovae. There is one more aspect of the collision scenario that deserves attention, and it concerns not the galaxies themselves, but the sky above whatever planet might still exist to witness it. If you could somehow stand on a world orbiting a star in the Milky Way billions of years from now and watch the approach of Andromeda, what would you see? At first, for billions of years, Andromeda would simply grow slowly brighter and larger in the night sky, gradually transforming from a faint smudge to a prominent, visible structure. As the distance closed to a few 100,000 light years, Andromeda would dominate the sky, an enormous spiral galaxy filling a significant fraction of the visible heavens, its spiral arms clearly visible, its bright core blazing. During the first close passage, the sky would be filled with the distorted, stretched shapes of both galaxies, tidal tails arcing across the sky, ribbons of gas, and stars pulled into dramatic bridges and streams. If the collision triggered a starburst, the sky would blaze with brilliant new stars and glowing nebulae. After the merger was complete and the elliptical galaxy had formed, the night sky would no longer show the familiar band of the Milky Way, that flat, disk-like distribution of stars seen edge-on from within. Instead, the sky would be uniformly filled with a soft, diffuse glow, the isotropic distribution of stars in an elliptical galaxy, surrounding the observer in all directions. But I must emphasize, no human being will witness this. If the merger happens, the median time is 7.6 billion years from now. Earth will be uninhabitable long before that. In roughly 1 to 1.5 billion years, the sun's gradually increasing luminosity will heat Earth's surface enough to trigger a runaway greenhouse effect, evaporating the oceans and sterilizing the planet. In about 5 billion years, the sun will exhaust its hydrogen fuel, swell into a red giant, and eventually shed its outer layers to become a white dwarf. Whether or not Andromeda arrives, the sun and Earth as we know them will be long gone. The Andromeda collision, if it happens, is a drama that will play out on a stage from which humanity, at least in our current biological form, will have long since exited. And yet, there is something profoundly moving about knowing this, not because it affects us directly, it does not, but because it reveals the nature of the universe we live in. Galaxies are not eternal, static structures. They are born, they grow, they collide, they merge, they transform, they age, and eventually they fade. The Milky Way is not permanent. It has already been reshaped multiple times by past collisions, and it will be reshaped again, whether by the LMC in 2 billion years, or by Andromeda in 7 or 8 billion years, or by both. The galaxy you call home is a work in progress, a dynamic entity in a dynamic universe. Now I want to pull back even further and place this story in the broadest possible context, because the collision between the Milky Way and Andromeda is not an isolated event. It is part of a pattern that pervades the entire universe. Galaxy collisions are not rare. They are not unusual. They are one of the primary mechanisms by which the universe organizes matter on the largest scales. The standard model of cosmology, the lambda cold dark matter model, or lambda CDM, describes a universe in which structures form through a process called hierarchical merging. In the early universe, small fluctuations in the density of matter, tiny regions where matter was slightly denser than average, served as seeds for gravitational collapse. These small overdensities attracted more matter through gravity, growing into the first dark matter halos, which in turn attracted gas that cooled and formed the first stars and the first small galaxies. These small galaxies then merged with each other to form larger galaxies, which merged to form still larger ones, in an ongoing process of growth through accretion and collision. The Milky Way itself was built this way, assembled from the mergers of many smaller galaxies over billions of years, as we have already discussed. Every large galaxy in the universe has a similar history of mergers. The Andromeda galaxy has been through its own series of collisions and absorptions. The giant elliptical galaxies at the centers of galaxy clusters, objects containing trillions of stars, were built through the successive merging of many large spiral galaxies over cosmic time. We can see galaxy collisions happening throughout the observable universe, frozen at different stages of the process, like frames in a cosmic flipbook. The antennae galaxies show an early to middle stage of a collision between two spirals, with dramatic tidal tails and intense star formation. The mice galaxies, NGC 4676, show another pair in the process of their first close approach, with long tidal tails extending from each galaxy, like the tails of mice. NGC 520 shows a more advanced merger, where the two galaxies have largely coalesced into a single, distorted structure. The Cartwheel galaxy shows the aftermath of a different kind of collision, a smaller galaxy that punched directly through the center of a larger disk galaxy, sending a ring of star formation expanding outward like a ripple in a pond. Each of these systems provides a glimpse of a different stage in the merger process, allowing astronomers to piece together the full sequence of events, even though any individual collision takes hundreds of millions of years to complete. But there is a tension in this story. If the universe is expanding, if galaxies are moving away from each other as space itself stretches, why are galaxies colliding at all? This is a question that strikes at the heart of modern cosmology, and the answer reveals something fundamental about how gravity and cosmic expansion compete. The expansion of the universe, driven by what we call dark energy, operates on the very largest scales. On the scale of hundreds of millions to billions of light years, the expansion dominates. Galaxy clusters that are far apart from each other are receding from one another, carried along by the expansion of the space between them. This is what Hubble's original observations of galactic redshifts demonstrated in the 1920s and 1930s. The farther away a galaxy is, the faster it appears to be receding from us. And since 1998, we have known that this expansion is not just continuing, but accelerating, driven by the mysterious, repulsive effect of dark energy. But on smaller scales, within galaxy groups and clusters, gravity can overpower the expansion. The local group, containing the Milky Way, Andromeda, and their retinue of smaller galaxies, is gravitationally bound. The mutual gravitational attraction between the Milky Way and Andromeda is more than sufficient to overcome the expansion of space across the relatively small distance of 2.5 million light-years that separates them. Within the local group, gravity wins. Andromeda is not being carried away from us by cosmic expansion. It is being pulled toward us by gravity. Beyond the local group, the situation is very different. The nearest large galaxy cluster, the Virgo cluster, is about 54 million light-years away, and it is moving away from us, though our local group is also being gravitationally attracted toward an even larger structure called the Great Attractor. On the very largest scales, everything beyond our local cosmic neighborhood is receding, and as the expansion accelerates, those distant structures will recede ever faster. In the far future, tens of billions of years from now, the accelerating expansion will carry all galaxy groups and clusters beyond our observable horizon. Their light will be redshifted to infinity. They will become, for all practical purposes, invisible and unreachable. This means that the local group, whether it remains as separate galaxies or merges into a single Milky Way, will become increasingly isolated. The rest of the universe will fade from view. A civilization existing at that far future time would see only their own galaxy, or merged galaxy group, in the sky, surrounded by the infinite featureless blackness of an empty, expanding cosmos. They would have no evidence that the rest of the universe ever existed, no redshifted galaxies, no cosmic microwave background. It would be stretched to wavelengths too long to detect. No indication that the universe was ever anything other than their one lonely island of stars. This is the ultimate cosmic context of the Milky Way-Andromeda collision question. Whether the merger happens or not, the local group is our long-term home, and eventually our long-term prison. Everything beyond it will be taken from us by the expansion of space. The question of whether we merge with Andromeda is really a question about the internal architecture of our cosmic prison. Whether it will be one big elliptical galaxy or two spirals orbiting each other in an otherwise empty universe. Let me now bring together the threads of everything we have covered and lay out the timeline of events as current science best understands it, incorporating both the well-established physics and the genuine uncertainties. We begin with the present day. Right now, the Sagittarius Dwarf Galaxy is in the process of being torn apart by the Milky Way. Its stellar streams wrap around our galaxy. It has passed through the Milky Way's disk at least 3 times in the past 6 billion years, triggering bursts of star formation each time. It will be completely absorbed within a few billion years. Approximately 2.4 billion years from now, the Large Magellanic Cloud will merge with the Milky Way. This is nearly certain based on current orbital data. The merger will increase the Milky Way's mass, may feed gas to the central black hole, and could temporarily transform Sagittarius A star from a dormant black hole into an active one. The LMC merger will also alter the Milky Way's trajectory through space, with potential implications for the Andromeda encounter. Approximately 4 to 5 billion years from now, if the collision follows the early arrival scenario, the Milky Way and Andromeda could have their first close approach. However, the Sawala 2025 study showed that the probability of this early dramatic encounter is only about 2%. It is possible, but very unlikely. Approximately 5 billion years from now, the Sun will exhaust its hydrogen fuel. It will swell into a red giant, engulfing Mercury and Venus, and possibly Earth. Eventually, it will shed its outer layers and collapse into a white dwarf. Long before this, Earth will have become uninhabitable due to the Sun's gradually increasing luminosity. The end of life on Earth, at least as we know it, will come in approximately 1 to 1.5 billion years, not from a galactic collision, but from our own star's evolution. If the Milky Way and Andromeda do merge, and there is approximately a 50% chance of this happening within 10 billion years, the median time for the merger is about 7.6 billion years from now. The process would unfold over several billion years. A first close approach, a flyby, the galaxies receding and then falling back together. A second close approach, more tidal disruption, and eventually a final coalescence into a single elliptical galaxy. The two supermassive black holes would spiral toward each other and merge over hundreds of millions of additional years. If the Milky Way and Andromeda do not merge within 10 billion years, and there is approximately a 50% chance of this as well, the two galaxies may continue to orbit each other for a very long time, possibly merging much later, or possibly never. They would remain as two separate spiral galaxies within an increasingly isolated local group. Over the next 150 billion years or so, regardless of the Milky Way-Andromeda outcome, all the remaining galaxies of the local group, but dozens of small dwarfs, the remnants of M33, whatever remains of the LMC and the Sagittarius Dwarf, would gradually coalesce into a single gravitationally bound structure. Whether that structure is Milkomeda plus accumulated dwarfs, or the Milky Way and Andromeda separately plus accumulated dwarfs, the end state is the same, a single entity, alone in the observable universe, as cosmic expansion carries everything else beyond the horizon. On even longer timescales, trillions of years, the last stars burn out. The remaining stellar remnants, white dwarfs, neutron stars, black holes, gradually cool and darken. The universe enters what physicists call the degenerate era, a vast, cold, dark expanse, punctuated only by the occasional faint glow of a cooling white dwarf or the invisible presence of a slowly evaporating black hole. But these timescales are so far beyond human experience, so far beyond even the current age of the universe, that they belong more to the realm of theoretical physics than to any story with practical relevance. Let me bring this back to the here and now, because there is a perspective in all of this that I think is worth sitting with for a moment. We live at a very particular time in the history of the universe. The universe is roughly 13.8 billion years old. The Milky Way is almost as old. Its oldest stars date to within a few hundred million years of the Big Bang. In its first few billion years, the Milky Way was a violent, chaotic place, growing through collision after collision. Kraken, Gaia Enceladus, the Helmy Stream's progenitor, Sequoia, and others we may not yet have identified. Then, about 8 billion years ago, the collisions stopped. The Milky Way entered a relatively quiet phase, building its thin disk, forming generation after generation of stars in an orderly, peaceful spiral. Our Sun, and with it, our Earth, formed about 4.5 billion years ago, during this quiet period. We are children of the peace between the wars. But the peace is not permanent. The Sagittarius Dwarf is crashing through us now, a reminder that collisions have not stopped entirely. The Large Magellanic Cloud will arrive in 2 billion years. And Andromeda, beautiful, massive, enormous Andromeda, is closing the distance at 110 kilometers every second. And whether it will miss us or swallow us whole is a genuine coin flip according to the best science available as of 2025. What I find remarkable is not the collision itself. Whether it happens or not, no human will experience it. What I find remarkable is that we can know about it at all. 112 years ago, Vesto Sliver pointed a telescope at a faint smudge of light and discovered it was barreling toward us. A century later, the Hubble Space Telescope measured its sideways motion with sub-pixel precision. The Gaia spacecraft mapped 2 billion stars and gave us the data to model the four-body gravitational dynamics of the local group's largest members. And in 2025, Tils Sawala and his colleagues ran 100,000 simulations and told us the truth. We don't know. But we know why we don't know. We know exactly which measurements need to be improved and by how much. We know the physics. We understand the forces at play. The uncertainty is not a failure of science. It is a triumph of honest science, a refusal to claim certainty where certainty does not exist. There is also something philosophically striking about the Milky Way's past. You, the person hearing these words, exist in part because galaxies collide. The atoms in your body were forged in stars. Some of those stars may have been born because of a galactic collision. When the Sagittarius Dwarf passed through the Milky Way's disk approximately 5.7 billion years ago, it compressed gas clouds and triggered a burst of star formation. Our Sun formed about 4.6 billion years ago during a period of active star formation in the solar neighborhood. Whether there is a direct causal link between the Sagittarius collision and the formation of our specific Sun is unknown and may never be known with certainty. But the broader point stands. Galactic collisions create the conditions for new stars to be born, and new stars are the prerequisite for new planets, new chemistry, and ultimately, new life. You are, in a very real sense, a product of galactic violence. And the galaxy you inhabit, the Milky Way, that quiet band of light arcing across the summer sky, is anything but the serene, eternal fixture it appears to be. It is a living structure, shaped by catastrophic collisions, scarred by ancient mergers, currently consuming a smaller galaxy, about to absorb another, and facing a future encounter with a titan that may or may not arrive. It is dynamic, evolving, violent, and beautiful, and for a brief cosmic moment, an eye blink in the life of a galaxy, we are here to understand it. The Milky Way's thick disk, puffed up by the Gaia-Enceladus collision 10 billion years ago. The stellar streams of the Sagittarius Dwarf, wrapping around the galaxy like a thread of fate. The globular clusters of Kraken, still orbiting on their ancient paths, carrying the chemical memory of a galaxy that no longer exists. The retrograde stars of Sequoia, orbiting backward against the flow of the disk, permanent foreigners in a galaxy they did not choose. The LMC, falling in for the first time, massive and inevitable. And Andromeda, 2.5 million light-years away, approaching at 400,000 kilometers per hour, its trillion stars and its 100 million solar mass black hole aimed in our general direction, and the universe refusing to tell us whether it will arrive or not. This is what it means to live in the Milky Way, not a static photograph on a poster, but a dynamic, evolving, colliding, merging, growing, uncertain, magnificent galaxy. And we are inside it. We are part of it. Every atom of our bodies was part of it before we existed, and will be part of it long after we are gone. Let me address one more thing before we conclude, because I think it matters. When people learn about the Milky Way Andromeda collision scenario, the most common reaction is fear. Are we going to be destroyed? Will the Earth be smashed? Is this the end of the world? And the answer is no on every count. Even if the collision happens, the stars pass through each other without contact. The solar system would be gravitationally reshuffled, perhaps moved to a new location, perhaps ejected from a galaxy. But in all scenarios, the Sun and planets remain intact as a system. And more to the point, Earth will be long dead before any of this happens. The Sun's increasing luminosity will make Earth uninhabitable within about 1 billion years. The collision, if it occurs, is a post-mortem event for our planet. There is nothing to fear from it, at least not personally. Not for any human being alive today or in the foreseeable future. What there is, instead, is something to marvel at. The scale of the forces involved, the elegance of the gravitational dynamics, the ingenuity of the scientists who have pieced together this story from photons of light collected by telescopes orbiting Earth and in space. The honesty of the 2025 study that said, "We have done the best job anyone has ever done on this problem, and the answer is that we genuinely do not know." The universe, it turns out, has not decided yet. Or perhaps it has decided, and we simply cannot read the verdict with our current instruments. Either way, the story is not over. It is being written in real time, in the slow, silent drift of 2 galaxies across 2.5 million light-years of space. The Milky Way is on a collision course. That much is measurably true. Andromeda is approaching us. The Sagittarius Dwarf is currently colliding with us. The LMC will collide with us in 2 billion years. These are facts, grounded in observation and confirmed by multiple independent lines of evidence. Whether the grandest collision of all, the merger with Andromeda, will actually reach its culmination is a question that hangs in the balance. A 50-50 proposition, suspended between the gravitational tug of 4 galaxies and the limits of human measurement. And that, in itself, is one of the most extraordinary things about our universe. After centuries of astronomy, after building telescopes that can measure the motion of a galaxy 2.5 million light-years away, to an accuracy of a few tens of kilometers per second. After running 100,000 computer simulations of the future of the local group, the honest scientific answer to one of the biggest questions about the fate of our galaxy is, we are not sure yet, but we are working on it. The Milky Way has survived every collision it has faced. It absorbed Kraken. It consumed Gaia Enceladus and was transformed by the experience. It is in the process of devouring the Sagittarius Dwarf. It will absorb the Large Magellanic Cloud. Whether it will absorb Andromeda, or be absorbed by Andromeda, or merge with it into something entirely new, remains to be determined. The answer depends on measurements that will continue to improve over the coming decades, as Gaia and its successors refine our knowledge of the motions and masses of our cosmic neighbors. For now, we are here, inside the Milky Way, riding one of its spiral arms, orbiting its center at 828,000 kilometers per hour, accompanied by the torn remains of galaxies past and the approaching masses of galaxies yet to arrive. The night sky above you is not a painting. It is a battleground, and the war has been going on for 13 billion years. If this video expanded your understanding of the universe, if it changed the way you think about the galaxy we call home, then it was worth making. Hit that like button, subscribe to this channel, drop a comment, and tell me the most surprising thing you learned today. Was it the fact that the Sagittarius Dwarf is crashing through us right now? Was it the Gaia-Enceladus collision that reshaped the entire galaxy 10 billion years ago? Was it the 2025 study that turned the certain Andromeda collision into a 50-50 gamble? I want to know what struck you the hardest. I read every comment. Share this with someone who loves space, who wonders about the universe, who deserves to know the real story of where we live and where we might be going. I will see you in the next deep dive into the cosmos. Until then, keep looking up. The answers are out there, 2.5 million light years away, and closing.